So with this video, we're going to be discussing about what exactly are vector embeddings and how they form the hard part of RAG, where RAG stands for Retrieval Augmented Generation. So vector embeddings are a way of representing words, sentences, images, or other data as numerical vectors in a high dimensional space. And this dimensional space could be as high as maybe even having 1,000 plus dimensions. So it's not your same old three-dimensional space, not your same old X, Y, and Z axis, but yeah, much broader than that, much larger than that. Now, these vectors capture the semantic or contextual information in the data, allowing similar items to be closer together in that space. So, the purpose of converting your images, sentences, and even words that you feed to your GPT engine uh, is to essentially capture the underlying semantic or contextual information that is contained in the data, and also to club together to sort of arrange similar items, similar words having similar meanings to be closer together in a particular confined space, uh, or the high dimensional space in this case that we're talking about. Now, how are these vector embeddings generated? What generates them? So these vector embeddings are generated by text embedding models that are offered by Azure OpenAI. And if I'm not mistaken, uh, the most common of these text embedding models is your ADA 002 model, which generates vector embeddings that are arranged in a dimensional space of having 1536 dimensions, so 1536 dimensions. And the more the number of these dimensions are, uh, the better you have captured the underlying semantic or contextual information that is contained in the data. So more dimension obviously means better understanding of the data, but uh, the engine is also going to cost you more, and the database that you would want to store these vector embeddings in is also going to incur a larger amount of cost. So there's a trade-off between having high dimensions and then looking for their applications as such. Uh, and these embedding models are deployed in the same way that you would deploy a GPT engine in Azure OpenAI resource, and these are built on a pay-as-you-go basis. So these are built on how many words, or rather, how many images or sentences in that case you want to vectorize. So again, talking about an example, let's say you have uh, the species canine, uh, and the sentence says canine companion say. Now this is a phrase. This is a phrase that is a combination of three words. Now, if you were to generate vector embeddings for this phrase, you send a request to an embedding model, which can be an ADA 002 engine in this case, containing the text in the body part of the request that you send your embedding model to, and it's going to return you vectors for the text that you sent as part of an API call. So you're gonna get back an array of floating point numbers. These are not integers, but these are floating point numbers which can range from minus infinity to plus infinity. And again, the same manner, we are sort of vectorizing the second phrase as well, feline friends say, and then generating vectors for this type of text. Now I talked about essentially generating vectors to capture the contextual meaning or the semantic meaning to sort of club together words having similar meaning or similar intent, right? Now, this is how you would uh, proceed to arrange phrases and words together based upon the type of semantic meaning or contextual understanding that they capture under the hood. So, if you notice a bit, if there's a phrase called as feline friends say, and because feline is the species for cats, they're obviously going to say meow. So that means that this phrase and the meow word is going to be arranged together. Similarly, canine is the species name for dogs, so canine companion say, and this phrase is gonna be arranged together with the word woof because dogs woof, right? And bovine buddies say moo. So bovine is the species name for cows. The phrase and the word moo is arranged together. But on the other hand, if you see this phrase, a quarterback throws a football, is altogether very different. It captures a very different semantic understanding and contextual information that is very, very, very different from the data set that we have arranged over here. So that's why it's in the high dimensional space that we are concerned about. It's placed far away from this cluster of phrases and words that we have got. And now this arrangement in high dimensional space is only and only possible through the help of vector embeddings. So this is a list of the various embedding engines containing models that are in general availability, and also models that are discontinued now. So these are legacy models as well. So if you notice, different vector embedding engines have different dimensions that they generate an array of vectors for, and you can also see the billing part for these embedding engines essentially. And if you notice, the higher the number of dimensions that it generates for me, the more it costs me per thousand tokens. So you must be noticing a word called as tokens. So tokens are nothing but, as in if you put in a text or a string of characters as part of an API call to these engines, be it embedding engines or GPT engines, those string of characters are converted to tokens via a token encoder. So uh, the reason being because they want to sort of wanted to find a way for calculating costs that they would apply for every call that you make to your GPT engine, and also it forms a very essential part of training these LLM models. And also because they wanted to define a contextual window uh, for each API call that you make to your GPT engine, as in they wanted to define how many number of tokens you can put into one single API call to your GPT engine. So this is the cost given per token for each of the embedding models that you wish to utilize. So again, this is a screenshot of uh, utilizing the text embedding ADA 002 model that returns you with 1536 dimensions of vectors. And what I did here is I took in a text, then uh, I first of all uh, took the description of the text as well. So let's say this text was section one short title, and there's some summary associated with the text. And I calculated the number of tokens for these corresponding texts and summary, and then I send a call to the ADA 002 embedding model. And this is how I got back a response with vector embeddings generated for me. So these are floating point numbers uh, of the embedding ADA 002 engines. And these are essentially going to be an array of 1536 vectors in total because ADA 002 returns you 1536 dimensions worth of vectors. So now the question is, how do I exactly store these vector embeddings in Azure? Is there a separate database or a separate storage option available for these? So the simple answer to that is yes. You have some native vector storage options in Azure, uh, but also you have the capability of building out of box solutions, your customized solutions. But if I were to speak about some native vector storage options in Azure, you have an Azure AI search resource, Azure Cosmos DB resource, which is right now in preview model for the day that I'm shooting this video on, and Azure Redis cache with vector similarity to handle caching of data. So speaking about Azure Cognitive or AI Search, Azure Cognitive Search is now rebranded as Azure AI Search, and it supports vector search, allowing for approximate nearest neighbor search on vector data. So it stores vector embeddings in a form of an index that works upon this algorithm called as ANN. Speaking of use case, it's ideal for scenarios where you need full text search combined with vector similarity search, such as recommendation engines or semantic search applications. So Azure AI Search supports the capability of performing hybrid search. And a beautiful uh, uh, functionality or capability of Azure AI Search is you can put in unstructured data and vectorize it with the help of Azure AI Search. What I mean by unstructured data is now this data can be in the form of either PDF documents, in let's say Word documents, or either in the form of .txt files, any unstructured data. And this data, let's say if you input a PDF document, this PDF document can contain images as well as text, and it's going to vectorize that for you. So that's one beautiful capability of Azure AI Search. And if I'm not mistaken, ChatGPT also uses Azure AI Search as the underlying infrastructure to build upon the beautiful user experience that it has. Features of Azure AI Search is it provides built-in indexing, similarity scoring, and integrates with traditional keyword-based search. So the Azure AI Search lets you perform hybrid search, in which hybrid search is a integration or a fusion of the traditional keyword-based search as well as vector search. Now, speaking of the second native vector storage option is Azure Cosmos DB. So Azure Cosmos DB is a globally distributed NoSQL database and has recently added support for vector search. It can store and retrieve high dimensional vector search. So let's say if you're using Azure Cosmos DB for NoSQL API, then in the same database, you can store your document and then your vector embeddings for that document structure as well. So that removes uh, the problem of running into building various ETL pipelines for extracting, transforming, and loading data into different data silos. The use case of Azure Cosmos DB is that it's suitable for applications needing high availability and scalability across multiple regions like real-time recommendation systems, and it offers built-in support for ANN indexing, provides low latency queries, and it also integrates well with various AI models and vector search. Now, third is Azure Redis cached with vector similarity. So uh, if you were to find a solution for storing vector embeddings for a small amount of data, maybe caching data, then you would go for Azure Redis cache. But if you wanted to store vector embeddings for a large data set, for a large amount of data, then you would go ahead with Azure Cosmos DB. So Azure Redis Cache has vector similarity search, and you can perform efficient vector-based lookups. It's suitable for caching and rapid similarity search, where low latency is crucial, like real-time recommendations or session-based personalization. And it supports similarity search with fast access times, but may need additional setup for managing large data sets. So this screenshot or architecture lets you visualize how you would make use of embeddings in a retrieval augmented generation architecture, where exactly they would come in and how they would play a crucial role. So for storing my data set, for storing my documents and in the form of JSON-like structure, and for storing vector embeddings in this RAG architecture, I'm making use of Azure Cosmos DB. So first of all, I'm importing some documents. Now these can be in the form of a JSON-like structure. Uh, and then I am breaking those documents, meaning uh, that I'm iterating over the documents that are stored, and I'm sending the data set of each document into the embedding model. Namely, it could be your ADA 002 engine. And then I get back embeddings from these models, and then I store the embeddings as well as the dataset of the documents in the Azure Cosmos DB database. So with this, we have successfully stored the document information as well as the vector embeddings for the data contained in the document. Now, in the third step, let's say the user enters a query, as in create a quiz with 10 questions based on XYZ data. I send this user query to my embedding model, for which I get back high dimensional vectors. So now what I'll do with the vectors that I've got for the user query is I will I will compare the vectors for this user query with the vectors that I have stored in the Azure Cosmos DB for the documents for the data that is contained in documents, and by performing algorithms such as cosine similarity or dot product, which we're going to have a look at once we do the demos. By making use of these algorithms and mathematical operations, I'm going to find for this particular user query the most relevant set of information that I can make use of to answer the particular user query. And then now that I have the contextual information derived from this Azure Cosmos DB database for the user query that was thrown, I will now send an API call to my chat engine saying, hey, this is the user query and this is the contextual information that needs to be taken into account while answering the user query. And now I need you to answer the user query back to the user. So I send an API call to the GPT engine and boom, I get back a response and I display that response back to the user. So this is how you can make use of vector embeddings in retrieval augmented generation. And this is how they form the very core part of RAG architecture. So that's pretty much it about the video. That was all about vector embeddings in general and how they come into uh, play when we are talking about retrieval augmented generation. So that's pretty much it from my side. With this, let's quickly move on to the next set of videos.